There is an ocean in our solar system that has been sitting in total darkness for 1 billion years. No sunlight has ever touched it. No wind has ever crossed its surface. It exists beneath 20 miles of solid ice on a moon so small you could drive across it in about 5 hours, orbiting Saturn at nearly 1 billion miles from the Sun. And in 2005, a NASA spacecraft flew close enough to watch that ocean blast itself into space through cracks in the ice, hundreds of miles high, at 800 miles per hour. That spacecraft was Cassini, and what it found inside that spray changed the search for life beyond Earth permanently. The moon is called Enceladus, and the reason it should terrify you has nothing to do with science fiction. It has everything to do with what science has already confirmed is down there in the dark on the ocean floor. Before Cassini arrived at Saturn in 2004, almost nobody cared about Enceladus. It was a footnote, a frozen ball of ice roughly 310 miles across, smaller than the state of Arizona, orbiting inside Saturn's faint E-ring. The Voyager spacecraft had photographed it in the early 1980s and noted that its surface was unusually bright, the most reflective object in the entire solar system, bouncing back nearly all the sunlight that hit it. But reflectivity alone doesn't get you a dedicated mission. Scientists assumed Enceladus was geologically dead, a cold, inert ice cube drifting in the outer solar system, interesting in theory, irrelevant in practice. Then Cassini's magnetometer picked up something strange during a routine flyby. The magnetic field around Enceladus was being disturbed. Something was bending it, deflecting charged particles in ways that a dead ice ball shouldn't be able to do. The Cassini team redirected the spacecraft for a closer look. When the cameras focused on the moon's south pole, they found the source. Enormous plumes of water vapor and ice particles were erupting through 4 parallel fractures in the ice, each one roughly 80 miles long, spaced about 25 miles apart. Scientists started calling them tiger stripes. More than 100 individual geysers were eventually mapped along those 4 cracks, collectively ejecting about 200 kilograms of material into space every second. Some of that material falls back onto the surface as snow, hundreds of meters deep in places. The rest drifts outward and feeds Saturn's E-ring. That ring, it turns out, is made almost entirely of Enceladus's ocean. The ice shell that covers Enceladus is not uniform. Globally, it averages somewhere between 20 and 25 miles thick. At the South Pole, where the tiger stripes are, it thins to as little as 1 to 3 miles. Beneath that shell sits a global ocean of liquid salt water, estimated to be 26 to 31 kilometers deep. For context, the average depth of all the oceans on Earth combined is 3.7 kilometers. Enceladus's ocean is roughly 7 to 8 times deeper than ours relative to its size, wrapped around a rocky core about 250 miles in diameter. The pressure at the bottom of that ocean, where rock meets water, depends on how you model the interior, but it's significant enough to keep the water liquid and dense at temperatures that on Earth's surface would freeze solid. No photon of light has ever reached the floor of that ocean. None. The ice above is miles thick. The nearest star, our Sun, is so far away that from Saturn's distance, sunlight arrives at roughly 1% of the intensity we feel on Earth, and all of it stops at the ice. Below the shell, there is only water, salt, rock, and absolute permanent darkness. The temperature at the ice-water boundary hovers near freezing, but deeper, closer to the core, things get warmer. The geysers alone prove that. Water does not erupt through miles of ice at 400 meters per second unless something below is generating serious heat. For years, scientists argued about where that heat comes from. The leading answer involves tidal forces. Saturn's gravity tugs on Enceladus as the moon follows its slightly elliptical orbit, squeezing and stretching the interior in a cycle that generates friction, and friction generates heat. A 2017 study published in Nature Astronomy by Gail Choblet and colleagues modeled this process and concluded that tidal dissipation within Enceladus's porous rocky core could produce enough heat to maintain the ocean for billions of years. The heat is not evenly distributed. It concentrates in narrow upwellings, hotspots where temperatures in the core exceed 90 degrees Celsius, focused primarily at the South Pole. And at those hotspots, something is happening at the ocean floor that should make you very uncomfortable. During Cassini's closest flyby of Enceladus on October 28, 2015, the spacecraft dove through the plume at just 49 kilometers above the surface. Its ion and neutral mass spectrometer and cosmic dust analyzer were running, tasting the spray as it passed through. What those instruments found went far beyond water. They found molecular hydrogen, they found carbon dioxide, they found methane, ammonia, formaldehyde, and traces of simple hydrocarbons. They found silica nanoparticles, tiny grains of silicon dioxide dioxide between 2 and 8 nanometers in radius. And in 2018, a team led by Frank Postberg at the Free University of Berlin analyzed Cassini's dust data and announced the detection of complex macromolecular organic compounds with molecular masses exceeding 200 atomic mass units. These were large carbon-rich molecules with multiple ring structures connected by chains of hydrocarbons, not amino acids, not DNA, but the kind of molecular architecture that on Earth shows up in environments where prebiotic chemistry is active. Then, in June 2023, Postberg's team published a paper in Nature that shook the astrobiology community. By reanalyzing archived Cassini data from ice grains collected in Saturn's E-ring, they had directly detected sodium phosphates, phosphorus, the last of the 6 essential elements required for all known life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Every other element had already been found. Phosphorus was the missing piece, and the concentrations were staggering. The concentrations were estimated to be at least 100 times higher than in Earth's oceans. Enceladus now holds a distinction shared by no other known body in the solar system besides Earth. It is confirmed evidence of all 6 elements considered necessary for biology. It has liquid water, it has chemical energy, it has organic molecules, and it has heat. Christopher Glein, a geochemist at the Southwest Research Institute who helped develop the phosphorus predictions, put it plainly: Enceladus is the only body besides Earth known to simultaneously satisfy all of the basic requirements for life as we know it. And what generates that heat, those chemicals, that hydrogen and silica, is a process that on Earth we associate with one thing: hydrothermal vents. Cassini found 3 separate lines of evidence for active hydrothermal venting on the floor of Enceladus's ocean. First, the silica nanoparticles. On Earth, nanoparticles of that specific size and composition form only in one way: when silica-saturated hot water rapidly cools after emerging from rock at temperatures above 90 degrees Celsius. Second, the molecular hydrogen. When hot water interacts with iron-bearing minerals in rock through a chemical process called serpentinization, it produces hydrogen gas as a byproduct. Cassini detected substantial amounts of hydrogen in the plume during its 2015 dive, consistent with ongoing serpentinization at the ocean floor. Third, the methane. The amount of methane Cassini found in the plume was higher than expected, and scientists could not account for it through any known non-biological process alone. Hydrothermal activity was the most plausible source. Together, those 3 lines of evidence paint a very specific picture. Somewhere at the bottom of Enceladus's ocean, hot mineral-laden water is rising from the rocky core through cracks and pores, mixing with cold ocean water and driving chemistry that, on Earth, sustains entire ecosystems without a single photon of sunlight. We know what those ecosystems look like. In the year 2000, researchers aboard the RV Atlantis discovered the Lost City hydrothermal field on the floor of the Atlantic Ocean, perched atop an underwater mountain called the Atlantis Massif at a depth of about 900 meters. Lost City is unlike the more famous black smoker vents. Its chimneys are made of white carbonate, not dark sulfide minerals. Its fluids are warm and alkaline, with a pH between 9 and 11, rich in hydrogen and methane. Some of its towers reach 60 meters tall, and it is alive, thriving actually. Microbial communities at Lost City run on chemosynthesis, converting hydrogen and methane from the vent fluids into energy without sunlight, without photosynthesis, without any connection to the surface world at all. These are organisms that eat rock chemistry. They metabolize the reaction between water and mineral, and they have been doing it for at least 120,000 years at Lost City alone. But Lost City is only one example. Across Earth's ocean floors, hydrothermal vents support communities of life that would seem invented if you hadn't seen them. Giant tube worms at Pacific vents grow to over 2 meters long and have no mouth, no stomach, no digestive tract at all. They survive entirely through symbiotic bacteria living inside their tissues that convert hydrogen sulfide into energy. Eyeless shrimp swarm around Atlantic vents, packed so tightly against the mineral chimneys that they pile on top of each other in writhing mats, sensing the heat through specialized organs on their backs where eyes used to be. Pompeii worms anchor themselves to chimney walls at temperatures exceeding 80 degrees Celsius, tolerating heat that would cook most known organisms. None of these creatures use sunlight. None of them know it exists. Their entire universe is heat, chemistry, pressure, and darkness. And the metabolic pathway at the foundation of many of these ecosystems, methanogenesis, combining hydrogen with carbon dioxide to produce methane and energy, sits at the very base of the tree of life on Earth. Some astrobiologists believe it may be the oldest metabolic process that ever evolved on this planet. The comparison between Lost City activity and Enceladus is direct and intentional. Nozair Khawaja, the lead researcher on the 2019 organic study, specifically cited Lost City when discussing his findings, noting that the evidence points to hydrothermal activity in the warm depths of Enceladus's ocean, not dissimilar from Earth's Lost City. If you're watching this and finding it interesting, consider subscribing. Every like and comment genuinely helps this channel keep producing content like this. Speaking of comments, if there's a topic you want covered, whether it's a specific ocean mystery, a creature, an expedition, a depth, leave it below. I read every comment and I actively respond to corrections and additions. The best video ideas on this channel have come directly from you. Now here's the part that makes this personal, at least on a cosmic scale. Enceladus's ocean is estimated to be about 1 billion years old. That number comes from modeling work by Marc Neveu and colleagues who simulated the thermal and orbital history of Saturn's inner moons using Cassini data. In their best fit scenarios, Enceladus's ocean formed roughly 1 billion years ago and has been liquid and chemically active ever since, maintained by tidal heating from its interaction with Saturn and the neighboring moon Dione. 1 billion years. On Earth, life appeared within the first 500 million years of the planet's formation, possibly sooner. The oldest confirmed microfossils are about 3.5 billion years old. The oldest chemical evidence suggesting biological activity dates to around 3.8 billion years ago, when Earth itself was barely 700 million years old, still being pummeled by asteroid impacts, with an atmosphere nothing like what we breathe today. Life didn't wait for conditions to be comfortable. It showed up early, possibly at hydrothermal vents on the ocean floor, in the dark, under pressure, surrounded by dissolved minerals and volcanic chemistry. If the same basic recipe, liquid water, chemical energy, organic molecules, mineral surfaces, and time is present on Enceladus, and all available evidence says it is, then 1 billion years is long enough. Not long enough for forests or fish. Long enough for the kind of life that started everything here. Microbial life, chemosynthetic life, organisms that would exist in permanent darkness, feeding on the chemistry of water meeting rock, completely unaware that such a thing as light even exists. Consider what that means. On Earth, every complex ecosystem ultimately traces back to photosynthesis, to sunlight. Even the deep-sea vent communities exist on a planet where photosynthesis oxygenated the atmosphere and filled the ocean with dissolved oxygen that supports the broader food web. Enceladus has none of that. If life exists in that ocean, it has never been supported by sunlight at any point in its history. There is no photosynthetic base. There is no dissolved oxygen from surface processes. Every calorie of energy available comes from geology, from the slow grinding of rock and water and heat at the interface between ocean and core. Life in Enceladus's ocean, if it exists, would be the purest expression of chemosynthesis anywhere in the known universe. Organisms sculpted entirely by the deep, with no evolutionary memory of a surface, no ancestral connection to light. Their biochemistry, their structure, their metabolism would have been shaped by an alien ocean with no reference point to anything on the surface of any world. That is a kind of isolation that makes the deepest trench on Earth look like a shallow swimming pool. And here is where Enceladus becomes truly unique among every potentially habitable world we have found. The ocean is leaking continuously. Right now, as you listen to this, over 100 geysers along the tiger stripes at Enceladus's south pole are blasting ocean water into space at 400 meters per second. That material rises hundreds of kilometers above the surface before some of it falls back as snow and the rest escapes into orbit, feeding Saturn's E-ring. The intensity of the eruptions is not constant. It fluctuates based on where Enceladus is in its orbit around Saturn. When the moon reaches apoapsis, its farthest point from Saturn, tidal stresses pull the tiger stripe fractures open, and the plumes brighten to roughly 4 times their minimum intensity. At periapsis, the closest approach, the fissures compress and the eruptions weaken. The moon is breathing, exhaling ocean water on every orbit, a cycle that repeats every 33 hours. And the entire E-ring, the widest and outermost of Saturn's visible rings, is made of ice grains that originated in that subsurface ocean. Every particle in that ring was once liquid water, sitting in the dark, in contact with Enceladus's rocky core, possibly carrying dissolved organics and traces of whatever chemistry is happening on the ocean floor. This means you do not need to land on Enceladus to sample its ocean. You do not need to drill through miles of ice. You just need to fly through the plume. Cassini did exactly that, multiple times, and with instruments that were never designed designed for astrobiology. It found organic molecules, phosphorus, hydrogen, silica, salts, and the chemical fingerprints of hydrothermal activity. Every major discovery about Enceladus's habitability came from a spacecraft that was built to study Saturn's rings and atmosphere, not to search for life on a 300-mile-wide ice ball nobody was paying attention to in 2004. The data that revealed phosphorus in 2023 was collected in 2004 through 2008 and had been sitting in NASA's planetary data system for over a decade before anyone looked at it the right way. Scientists are still combing through Cassini's archived measurements. Khawaja himself said there are spectral types in the data that he sees and still cannot explain. There are signals in the archive that nobody has interpreted yet, and those signals came from a spacecraft that could only taste the plume as it flew through at kilometers per second. A dedicated mission built for the job, orbiting Enceladus, repeatedly sampling the geysers with instruments calibrated to detect amino acids, lipid membranes, metabolic byproducts, even individual cells, would be operating in a different category entirely. Several such missions have been proposed. The Enceladus Life Finder, the Enceladus Orbilander concept from Johns Hopkins Applied Physics Laboratory. ESA has assessed mission architectures. None have been funded for flight as of today. There is no confirmed return mission to Enceladus on any space agency's active manifest. The ocean that has every ingredient we know of for life, the ocean that is voluntarily handing us samples of itself through cracks in the ice, remains unvisited since Cassini's final flyby in December 2015. That was over a decade ago. The geysers are still erupting, the ocean is still warm, the chemistry is still running, and no one is going back to check. On the floor of a dark ocean a billion miles away, where hot water meets ancient rock and hydrogen rises through cracks in the seafloor, conditions exist right now that are functionally identical to the environments where life began on Earth. We know this because we flew a spacecraft through the exhaust and read the ingredients list. And the most unsettling part of all of it, the part that should keep you up, is that the answer might already be in the data we collected 20 years ago, sitting in an archive, waiting for someone to look at it the right way. Thanks for watching, and I'll see you in the next one.